Let's discuss another very important concept, that is sound waves as pressure waves. Very soon we are going to see that sound waves are also termed as pressure waves because when sound propagates in a medium, the pressure of medium varies periodically and the phase at which the pressure varies is also propagating at the same speed as that of sound waves. And we can start with the fact that we already studied, as we know, that in longitudinal waves, medium density varies periodically. This we have discussed that for a simple harmonic sound wave, compression and rarefaction zones propagate at the same speed as that of speed of sound. We once again analyze the similar situation. So this is a direction x in which a simple harmonic wave is propagating, and say we draw a displacement curve. So this is the displacement curve of the wave which is propagated in x direction at a speed v, and in this situation say we pause the wave at a particular situation when medium particles O, A, B, C, D, E are at their mean position, and these crests and troughs are propagating at a speed v. If we just analyze the same situation on the actual medium, if we talk about the actual medium, we can see that the points O, A, B, C, D and E, these must be located at their mean position. And if we talk about all medium particles between O and A, these are having some positive displacement. So these are all drifted towards point O at this instant when we are just looking at this displacement curve. So here we can say majority of medium particles between O and A are located in the neighborhood of A. And all particles in between points A and B are having negative displacement. So these are in the neighborhood of A again. So we can say A is a point of high density or compression, where we can say as density high, the pressure will also be high. So there's a high pressure point. Similarly, point B, we can see all particles on the left of B are shifted away. All particles to the right of B are also shifted away. So point C will also be a point of compression. Similarly, point E will also be a point of compression where majority of medium particles are located. So these are the points of you can say high pressure, and point O, point B and point D are those where medium particles are drifted away from these locations. So the zones in the neighborhood of point OBD are low pressure zones because the density is low. These are low pressure zones. Now as the wave is propagating in x direction, here we can say these compression and rarefaction or high or low pressure zones are traveling forward with the speed v. So if we talk about any point say M, at this point right now you can say the medium particle is at its extreme position. So here the density is moderate because on one side density is slightly higher, on left side it is slightly low. So this is the point where pressure is atmospheric. But as the wave propagates, this point of rarefaction will reach here and its pressure will decrease. When this compression will reach here, pressure will increase. You can perceive that at this point or at every point in the medium, pressure will increase, decrease above and below the atmospheric pressure level with some pressure amplitude or the maximum pressure up to which it will move up and it will go down. So we can state at every point pressure varies periodically and the phase of pressure is propagating in the direction of sound at the same speed v. Let's mathematically analyze the maximum pressure and minimum pressure which are developed at compression and rarefaction. Let us discuss the pressure variation analysis in a sound wave. Say if we consider a zone which is of cross-sectional area S, in which the sound wave is propagating at say a speed v. In this situation, all the medium particles in the zone would be oscillating forward and backward along the direction of propagation as sound waves are longitudinal. We consider an element of width dx in the medium, and the edges of dx are named as 1 and 2. Then all the particles on one side of this element dx, these are at position x. So these would be oscillating forward and backward. Say at any instant, if we talk about its displacement as a function of time and position, we can write simple harmonic wave equation for this position x. We can write it y is equals to a sine of omega t minus kx. Now in this situation, if for this elemental displacement dx, say these particles which are located at point 1 are displaced by a displacement dy, then we can say this volume which is having a length dx cross sectional area s is compressed by a distance dy, where dy can be given as, simply we can differentiate it, gives us minus ak cos of omega t minus kx dx. Here we can say this is the volume by which this total volume is compressed. So here we can simply calculate the volume compression in length dx is, which is due to the propagation of wave. This can be written as dv, which can be written as s dy, and this and the total volume, this volume is s dx, in which this compression is there, which is s dy. We substitute the value, we can get it minus sak cos of omega t minus kx into dx. Now from here we can find out the volume strain in this element. We calculate the volume strain, it is given by dv by v, and this volume strain we can calculate from here. This dv by v will be minus ak cos of omega t minus kx. This is the volume strain. And if we find out the bulk modulus of the medium in which the wave is propagating, then we know that bulk modulus can be given as B is equals to excess pressure divided by volume strain, which is negative of dV by V. We substitute the result here. You can find out the excess pressure at the position X, from where we can find excess pressure at position X in medium. This can be given as delta P is equals to B multiplied by volume strain. So this will be BAK cos of omega t minus kx. This is the expression we are getting, and this BAK we can write the maximum variation in pressure. So this expression can be written as delta P naught cos of omega t minus kx. So you can see that delta P is giving us excess pressure at a position X, and as a function of time it is periodically varying, and here delta P naught is a maximum pressure variation called pressure amplitude for sound waves. Let's analyze the expression further. As just now we have obtained that the excess pressure in a medium where sound wave is propagating is given as delta P naught cos of omega t minus kx, where this delta P naught we can write as BAK, where k is the angular wave number, we can write it 2 pi by lambda AB. Just keep the result in your mind. This is the pressure amplitude of the sound wave, which is the maximum pressure variation in a sound wave at the positions of compression, rarefaction, and at other point the pressure is periodically varying, which is between atmospheric pressure and the maximum or minimum pressure. If we just analyze this practically, we can compare it with the displacement curve of wave also. Like if I draw the displacement curve of a simple harmonic longitudinal wave, it looks like this, where points are O, A, B, C, D, and we just compare it with the actual medium also. In actual medium, we already studied that A is the position where on left hand side all particles are having positive displacement, these are towards A, and between A and B all particles are having negative displacement, so these are displaced towards A again. So by the same analysis here we can say that A and C are the points which can be considered as points of compression where most of medium particles are accumulated, and at points O, B and C, these are the medium particles in the neighborhood of which medium density is less. So we can say at point A density is maximum, pressure will be maximum. It can be written as atmospheric pressure plus delta P naught, where delta P naught is this pressure amplitude, and at point P pressure is minimum, which can be given as atmospheric pressure minus delta P naught, where again delta P naught is the pressure amplitude. And those points which are corresponding to extreme positions, we can see at these positions the pressure amplitude will be given as only P naught, as at this point this delta P is equals to 0, because these are the points where sin omega t minus kx is 1, so cos omega t minus kx will be 0, so here delta P is 0. So when we talk about the medium particles which are corresponding to extreme positions of oscillations, there the pressure in the medium is exactly equal to atmospheric pressure P naught. Here we are taking atmospheric pressure in the medium, the normal pressure in the medium to be equals to P naught. So in this situation, as the wave is propagating forward with the speed v, at every point when compression will come, the pressure will become maximum. When compression passes on and rarefaction will come, the pressure will become minimum. Here we can see that the displacement equation can be given as A sine of omega t minus kx for a simple harmonic wave. Its pressure variation equation can be given as delta P naught cos of omega t minus kx. You can see that in displacement and pressure variation at any medium particles in a simple harmonic longitudinal wave, we can write that phase difference is equals to pi by 2. So this is the basic analysis how pressure varies periodically. At any point where position is x, we can write pressure is equals to P naught plus delta P, where delta P is periodically varying, which can be written as delta P naught cos of omega t minus kx. This is the equation for pressure at any point.